Good evening and once again welcome to my YouTube channel, Pearson with Excel International Math by Mitakamoto. And today I want to wind up on chapter 1 of Pure Mathematics 2. Pure Mathematics 2, and the topic is algebraic methods, and we'll be looking at counterexample. And a mathematical statement can be disapproved using a counterexample. And for example, to prove that the statement 3n plus 3 is a multiple of 6 for all values of n is not true, you can use the counterexample when n is equals to 2. As of course we are saying that to prove that the statement 3n plus 3 is a multiple of 6 for all values of n is a multiple of 6 for all values of n. If you want to prove this, probably you may challenge it by simply talking about one example. What about when n is equals to 2? So 3 times 2 plus 3 is by itself 6 plus 3, which is 9, and 9 is not a multiple of 6. So it has been the original statement has been disapproved. You can prove a mathematical statement is not true by a counterexample. Of course, a counterexample is an example that does not work for the statement. A counter is an example that does not work for the statement. This is true. And I want us to just go to example 16, so to speak. Yes, hold on. Prove that the following statement is not true. Prove that the following statement is not true. That the sum of two consecutive prime numbers, the sum of two consecutive prime numbers is always even. Well, disapprove this. You know, when we have just a 2 and a 3, these are two consecutive prime numbers. The sum of two consecutive prime numbers is always even. Of course, we know 2 plus 3, which are qualified to be two consecutive prime numbers, is 5, and 5 itself is not even. So already we have disapproved the statement by giving a counter example. And if you go further to example 17, let's talk about example 17. We are told that prove that for all positive values of x and y, that x over y plus y over x is greater than 2. And that is part A. Well, we are supposed to prove this. Of course, it goes without saying that the two numbers on the left are fractions, and they are being added together. So it is very important to ensure that we need to collect what we know. The LCM at the denominator is xy. Xy divided by y is x times z is x squared plus y squared. Of course, this one gives you greater than or equals to 2. So if you open the bracket, not just the bracket, if you cross multiply, you're going to have something about x squared plus y is greater than or equals to 2xy. If you take this to the left hand side, at least to give us something we know, is going to be x squared plus y squared minus 2xy is greater than or equals to 0. This statement is very familiar to all of us because it gives us something that we already know, that it's a difference between two squares, and if you factorize out, we're going to have x minus y squared is greater than or equals to 0. So this one is the beginning of our proof, because we know any expression squared is 0. This is an expression when any number is squared, obviously greater than 0. This is a fact. This is a known fact. So this is a valid way to begin our proof. And what are we simply saying? That if we talk about x plus y squared minus 2xy greater than or equals to 0, and we realize that we can divide everything by xy. If we divide both sides by xy and even this side by xy, only that you're going to have x squared over xy plus y squared over xy minus 2xy over xy, of course greater than or equals to 0, because 0 divided by xy is simply 0. And of course, this one will give us x over y plus y over x over y plus y over x minus 2 is greater than or equals to 0. So if we attempt to make now, to let minus 2 cross over, is going to be x over y. It's going to be x over y plus y over x is greater than or equals to 0. And hence shown, this is what we are supposed to prove. And therefore, we have proven that one. Okay, we are getting back with part B, so be on the lookout for part B. Okay.